All right, so after we have data, then its analysis, the analysis of the data, the interpretation of the data, and you hear this a lot. Collecting the data is one thing, but how you interpret it is a completely different story. And so it's just as critical. And making sure that you follow standard models and are aware of what people are doing when they're analyzing the data is very important, right? And that's never been better represented to the community than, to the world, than the coronavirus scenario right now. The media just grabs numbers and puts them up there from so many different perspectives. It's almost impossible to know exactly what the numbers actually are representing. Okay, so let's look at section 1 here. Let's consider a scenario where we want to know what the mass of a penny is. Now, a penny might mean something to different people, right? It might mean 1/10 of a Canadian dollar, or sorry, 1/100th of a Canadian dollar, 1/100th of something in a European country. But we're going to talk about a United States penny. All right. It also, we have to narrow down to, are we going to care about pennies made at different mints because pennies are made at different places? Are we going to care about the fact that pennies changed their mass from the 1960s, 1950s to 1990s and so forth? So we kind of have to be a little more precise. But if we talk about pennies that are in circulation currently, and we want to kind of characterize the mass of a penny, we would collect the mass of a subset. We wouldn't be able to collect the mass of all the pennies, right? That would take too much time, and we don't have access to them. Impossible. But we want to collect a subset. In fact, really what we want to know is how few can we do and really get a decent number? Or based on how many we collect, can we have an approximation of how accurate our resulting findings are? Okay. So, one of the parameters that we use to kind of identify the actual value is the mean, or the average. The average, you know how to take the average, Fred?
Yeah, you just add them all up and then divide by how many there are.
That's right, and that's what this little equation here says. Adding up all of them and dividing by how many there are. Very good. Now, there are some weaknesses to the average, and I trust that you could perform this sort of an experiment. I want to see that you can do it in Excel. Okay, so if you've forgotten how to do that, we'll have practices later on, but that's something, we're always going to be taking the average, and as we go further down here, the standard deviation in Excel. But there are some drawbacks, some trade-offs for using the average as an estimation of the actual value. One of those is if your values are off. For example, if you put in a value like 31.07 on accident, 31.07 as opposed to 3.107, the mean changes drastically. Okay? The median helps avoid that. The median is just a lineup of the numbers from smallest to largest, and then you look at the middle one. If you don't have a middle one because you have an even number of measurements, you take the average of the middle two. The median is not as susceptible to huge errors, right? Now, you can think, well, just don't report the error wrong. But the error also something could go wrong in an experiment where it's not the reporting component, but something in the experiment that went wrong as well. So, we have our mean and our median. Then there's 3 different measures of the spread for a set of data. The range is the largest minus the largest value minus the smallest value. Okay, and that has its contribution. It's not really used much. The standard deviation is probably what's used most and what we're going to use in our class. Okay, Here is the standard deviation. This is basically looking at every x value, subtracting it from the average, squaring it, summing that all together, dividing by the number of samples you have minus 1, and then taking the square root. That's the standard deviation. The relative standard deviation is that value divided by the mean. Okay? And then you multiply it by 100 and you get the percent standard deviation. Okay? So this business here, standard deviation, relative standard deviation, is important. But once we do it in Excel and always allow Excel to do it for us, then it's really not a huge burden, right? We don't have to really think about it too much. We do want to be aware of what it is, and it is a good tool to measure your precision, right? The average is a good tool that measures the mean is a good tool that measures the accuracy, but it doesn't represent the precision very well. So a combination between the average and the standard deviation is pretty good at measuring the accuracy and precision of a measurement or a set of measurements. The variance is what we call is the square of the standard deviation, used in some instances but not going to be used by us. Okay, not much at least. All right, very good. Errors, 4.2 now, errors that affect accuracy, right? Our accuracy, again, can be determined by taking our average minus what we call the expected value, or the true value, okay? The average here, x bar, the true value, mu, and then the error, absolute error, like we mentioned this before, which we can convert to relative error by dividing by the actual value there. Okay? Now, oftentimes we don't know the actual value, right? Do we know the actual average mass of a penny?
I don't, but you could, right?
Could you?
Well, I guess we decided we couldn't get every penny, could we?
That's right, and we can't weigh them all, so we would never be able to know the actual value. However, there's a number of pennies that you'd have to weigh to get a value that would not change once you continue to add more and more pennies. Does that make sense?
Not really.
Well, if I took an average of 20 pennies, let's say, and I knew the average of those 20 pennies, if I added the 21st penny, do you think it would change the average?
I don't know. What do you think?
It probably won't change the average because the average has already been influenced by those 20 measurements, so the 21st is not going to be changing things. Okay? So, identifying that number in terms of the number of measurements we can take without changing the average, or the minimum number of measurements, and also identifying the error associated with our actual value based on the limited number of measurements. So even if we knew, if you measure this 20 times, you'll get a value that is very, very close to the average, we'll be limited by many parameters in such that we generally only use 3 or 4 measurements, 3 or 4 experiments to use or get an average.
Okay.
So, all right, so determinate errors. Determinate errors are errors that are affect our accuracy. And these errors are generally not always the same within each measurement. They are not considered random errors. They will shift the average positive, or it could shift it negative. The accumulation of these errors is going to be net positive or net negative in terms of its accuracy. Sampling errors are an example of determinate errors. If you're making error, if you're making sampling in the wrong location, we talked about the lake, right? You can read through that little section right there. Method errors, right? A method error exists when our Ka or our SMB in this equation here, so our total signal is due to Ka times Ca, right? That's something we've talked about a lot. But if we also include the signal due to the method blank, right, then the total signal should be fine if the method blank is taken out of the equation, right? If it's essentially 0. But if Ka is not correct, or if SMB are not correct, then we're going to get errors in our method. Okay. Measurement errors, right? If you're measuring the wrong volume, we have a good list here of tolerances of what we call type A volumetric glassware. Type A volumetric glassware, those are our, and they say on the side, volumetric pipettes, volumetric flasks. They don't need calibrating because their error is very minimal. All right. You have type B glassware that's out there, and then you have other types, such as beakers, graduated cylinders. They're not going to be very effective for measuring volumes accurately. Here's a table, a nice table for measuring errors of digital pipettes, and one for our selected balances, or some balances, right? And this sort of thing, information comes with the balance, so it's nice to have available to you. Personal errors. Now that sounds like a dirty word.
What does that mean?
Well, that means that the person is making the error, right? Which is a problem. Now, identifying determinate errors is important, and trying to remove those errors. That's why we have standards to work on until we figure out what's causing the error, and then we can try to remove it from the method. So this is an example of how the mass of the sample affects the determinate error, right? So if this is the actual true value here, one good way to get rid of your determinate error is to make sure you work with a large sample, right? And I've had that experience throughout my life. When things go rough, just sacrifice a lot of sample and try to figure out where your issues with your experiments are. Sometimes you get what's called a proportional determinant error. If you use more and more sample and you see that the error gets worse, then that is also a way that you can figure out where your error is coming from, or what the source of your error is. Okay. An indeterminate error. Indeterminate error. These are errors that are not going to be really easy to recognize, and generally they do not alter the average or the measurement, the actual resulting measurement value that you have, because they are random, both positively and negatively. Okay, so we call an experiment repeatable when the precision of a single analyst completes an analysis in a single session using the same solutions, equipment, and instrumentation. In other words, somebody else can do the exact same thing, exact same way with the same instrumentation. Repeatability. Reproducibility is the precision under any other set of conditions, including between analysts, laboratory session, for one given analyst, or one given analysis, one given type of method. So repeatability means the same person can do it over and over. Reproducibility means you can go to a different person, slightly different instrumentation, and still get the same values. So how do we evaluate indeterminate error? Or sources first. Sources of indeterminate error. There's many, right? Collecting, like we mentioned, manipulating samples, making measurements, all sorts of different sources for these indeterminate errors. Indeterminate errors will affect standard deviation, right? Because kind of random spread around the actual value. You can try to evaluate the effect of the indeterminate measurement errors on your samples. For example, if we talk about the penny, right? We might have several indeterminate errors. You can take the same measurement 4 times, for example, and try to find the standard deviation on that same measurement, and that would be a good source to determine your indeterminate error. All right. Okay. Error and uncertainty. Uncertainty expresses the range of possible values for a measurement or result. All right. Know that this definition of uncertainty is not the same as our definition of precision. Okay. We calculate precision from the experimental data and use it to estimate the magnitude of indeterminate errors. This is an example to help us see this between precision and uncertainty. So if you purchase 10 milliliter class A pipette from the laboratory and use it without additional calibration, the pipette's tolerance is 0.02 milliliters. That's its uncertainty, because your best estimate of its expected volume is 10 plus or minus 0.02. This uncertainty primarily is determinate. If you use the pipette and dispense several replicate samples and determine that the volume of the deviation is 0.0006, then that can be used as its, it's different. That standard deviation is different than the uncertainty. The standard deviation is the precision with which we expect to deliver the solution. In the case of the pipette, the published uncertainty is 0.02. It's going to be worse than the standard deviation. So here is a table here. These are experimental results for volume dispensed by a 10 milliliter Class A transfer pipette. And these are our multiple replicates, our multiple values here, right? And so from this data, we can use it to, let's use this data here to look into Excel and try to learn about the standard deviation. So some of you don't know how to do standard deviation, or I'm sure most of you do, but we need to begin to become familiar with Excel. Now, a lot of you are going to want to use Google Sheets, but you shouldn't. And I'll never accept an assignment in Google Sheets. You need to provide the assignment, any spreadsheet assignment needs to be done with Excel.
Why is that?
Well, Excel is the standard, right? There are other plotting softwares, and they're mentioned in this book, and I haven't experienced a lot of them. But I learned early on from my experience as a student. I actually tried a couple of the ones that they suggest. The ones that they suggest are constantly evolving and improving. But because I was poor as a student, I chose to work with an open office spreadsheet, right? And it was fine, and I learned things. But the things that I really learned the most were the differences between Excel and the open office. And that's not what we're trying to do here. We're trying to prepare you with standard skill sets that will translate very well into whatever lab you go to. If you have a general understanding of Excel, there's a likelihood, and it's relatively high, maybe more than half of the labs that you go to are going to be utilizing different kinds of software. But your standard understanding, your general understanding of Excel will provide you what you need to be successful in those new types of software. Okay, so let's look at this data here and try to get it into Excel for ourselves. Let's see, is this going to work? So it didn't work to paste it right into Excel, but if I paste it into Word, so I chose the text option. If you go in here to keep source formatting and merge formatting, if I choose the text only option, then I think that this is going to be able to then copy well into Excel. Let's see if I'm right. Yeah. So that's really convenient. I can just take the information straight from the textbook and get it into Excel. All right. So I'm going to put these all into one data set here, 1 through 10. Okay, and now I'm going to remind everybody how to take the average, right? So we have 10 values here. So if I write an equal sign and then start typing the word average, whoops, A-V-E-R, then the first one here, just average, not average A and average if and average if S. I don't know all the different ins and outs of Excel, but we'll stick with the ones that I introduced to you here in terms of average and standard deviation, and we'll be fine. Maybe I'll provide an assignment where you kind of explore what the different standard deviations are. But so I double click on that one and then highlight my values, and then I just push enter, and that gives me my average. And it's nice to label this average like that. Now the standard deviation. Now, do you remember the tolerance on these measurements, on the instrument that you made these measurements?
The tolerance?
Yeah, the uncertainty here.
Oh yeah, 0.02.
That's right. So 0.02 was our uncertainty, but we're going to find out what our standard deviation is here. Let's see. Oh, so this time here, same thing. I'm writing the equation for the standard deviation, STDEV, and then I can just double click on this one here, this first one that says, or not the first one, but the one that says STDEV without anything else. So I double click on it, and man, look at all those different types of standard deviation. I don't know exactly what they all are. So we'll all use this STDEV one. Highlight the values here like that, push enter, and that gives me my standard deviation. Okay. This is a standard deviation. The percent standard deviation would be, this is so that, you know, this is a plus or minus value. I can use this as a plus or minus value. So I can say when I deliver 10 milliliters with this tool, I deliver 9.9915 plus or minus 0.006. Okay, and also one thing that we might talk about later, but I'll introduce it to you first or here right now, is this 0.006 shows that that 6 is the first. Let me see if I can zoom in a little bit here. Is the first, that 0.06, that 6 right there is the first value of my deviation, right? So I have a deviation value in my third decimal place. So although I have 4 decimal places, 4 points beyond the decimal place here, 0.9915, if I have a deviation of 0.006 in my, this is my tenths, my hundredths, my thousandths place, then it doesn't make any sense to report 0.9915 because that 1 is the place where I already have the deviation. So it doesn't make sense to report that 5. Does that make sense?
I think so.
So this 6 here is my first, indicates my first decimal place that I have deviation in. And so I don't want to report more decimal places beyond that deviation. So in this example here, I should have room for all 5 of these significant figures. But another thing that can cut off significant figures is your error or your deviation. So I can right click here and say format cells and report because of that, or just make it a number and report only 3 significant digits. So now I can say that my value is 9.92 plus or minus 0.006. And again, it isn't very helpful to know that 0.1 or 0.613. If this value is going to be all the way up to plus 6, this 2, so 9.998, and all the way down to minus 6, 9.984, right? Then who cares what's going on over here with this 1 and this 3? So this one here, I can format, and where do I want to cut it off? How many decimal places do I need there?
Just the 3.
That's right. 1, 2, 3 decimal places there. So there we have it. That's my average, and that's a good standard deviation. Okay? Very good. So hopefully, whoops. Oh, here we go. So hopefully that is going to be a good reminder of how to do take the standard deviation. I'm not interested in you learning how to take your standard deviation in your calculator. I think that it's good to work in Excel here. The average, everybody knows how to take in your calculator, which is fine, but that also I prefer you to be doing in Excel to get the experience that you need in Excel. All right, very good. Where are we at? Is this 4.6? 4.2. All right, so now moving on to 4.3, propagation of uncertainty.